Now we're going to turn our attention to what are called rational functions. Rational functions are just the ratios of polynomial functions, so it makes sense to talk about them since we just talked about polynomial functions. We'll be looking for the same information about a rational function as we do about really any function. What are its domain and range? We'll look for the intercepts, and then rational functions have a feature that not all functions have, and that's called horizontal and vertical asymptotes. So we'll also be looking for the asymptotes of these functions, and then we'll solve some applications involving these rational functions. So, as I said, we'll start with the definition, and that just says that a rational function is any function of this form, r of x equals p of x over q of x, where p and q are polynomial functions. So the functions we just looked at in the previous video. So the ratio of two polynomial functions. So a few examples here. The first one, f of x equals 3x plus 2 over 5x squared minus 7. We have a degree 1 polynomial in the numerator, a degree 2 polynomial in the denominator. It's simple to see that that's a rational function. The next one, we have g of x equals 2 over x squared. So 2 is a degree 0 polynomial, still a polynomial but a very simple one, just a constant. X squared is a monomial, but it's certainly a degree 2 polynomial. H of x, what we've got is factored forms of the polynomials in the numerator and the denominator, but still we do have a polynomial in each location. So we'd have a degree, looks like 6, because we have 6 factors involving x, over a degree 2 in the denominator. We've already graphed some rational functions, one of them being just 1 over x. That's in our library of functions, a very simple rational function. Let's just recall what that graph looks like. So it has the points 1, 1, negative 1, negative 1, and then it has a vertical asymptote on the y-axis and a horizontal asymptote on the x. X is not allowed to be 0. And because we always have 1 over a quantity, y will never be 0 because there's always the 1 in that numerator. So that's the graph. The domain is all reals except 0. And the range is all reals, but these are y values, but except for y equals 0. The horizontal asymptote is the x-axis, which is the line y equals 0, and the vertical asymptote is the y-axis, which is the line x equals 0. Notice that it's important to write the y equals or the x equals. You don't want to just write 0 because then it's not clear whether you have a horizontal line or a vertical line. So let's just take a look at a more formal definition of this asymptote word. So the line x equals any constant is a vertical asymptote of the function. It says if y is going to infinity or y is going to negative infinity as x gets closer and closer to a from either side. So if we have, let's say this is x equals a, if on the left or the right the function values are going up or down, that line is a vertical asymptote. Right, so as x gets closer to a from either direction, from the left or the right, the y values are approaching infinity or negative infinity. So if any of these things are happening, then that line x equals a is called a vertical asymptote of the function. the line y equals b is a horizontal asymptote of f if, as y gets closer and closer to b, as x goes to the right without bound or to the left without bound. So for the horizontal asymptotes, we're just looking at x getting large positive or x getting large negative. And if the function values get closer and closer to that line, on either side, so as we move to the right or as we move to the left without bound, then that line y equals b is called a horizontal asymptote of the graph. So we want to start graphing these things. The first one, we're going to use our graphing calculator to get a graph of this function, and we're going to look at all the key features. Let's figure out which of these we could solve for without a graphing calculator, and then use our graphing calculator for the others. Our x-intercept would be when the function is 0. So let's see what we can do with that. So we would set the y value, or the output, equal to 0. If we multiply on both sides by x minus 4, then we have just 0 equals 3x plus 8, which means x will be negative 8 divided by 3, which is what, negative 2 2/3. So we should see an x-intercept between negative 2 and negative 3. A vertical asymptote, if you think back to the graph of 1 over x, the vertical asymptote was x equals 0, which was the 0 of the denominator, the place where the function is undefined. So when we're looking for the vertical asymptote, we want to know, where is the function undefined? And in this case, that would be when x equals 4. So the equation of the vertical asymptote, it's a vertical line, so it's an x equals something. It would be x equals 4. The y-intercept, that's f of 0. And that means put 0 in for x. So 8 over 0 minus 4 would be 8 over negative 4. So negative 2. So we've got a y-intercept at 0, negative 2. For the horizontal asymptote, at this point we'll use the graph to see. That's not something we can at this point know in advance, but we'll talk about how to figure that out in a minute. But at least we know we're expecting an x-intercept at negative 2 2/3, so over here. And we're expecting a vertical asymptote at x equals 4. So let's draw those in. And we also know the y-intercept is 0, negative 2. Okay, so then let's pull up a graph for the rest of it. 3x plus 8 over x minus 4. Be very careful when you enter these onto your calculator. Put parentheses around the numerator and around the denominator. So make sure you enter it just like that. And let's make the window for the graph the same as the window we're looking at here. So negative 8 to 8, negative 8 to 8. Alright, and it looks like we see this branch coming down through quadrants 2, and then a little bit in 3, and then into quadrant 4. And it looks like we can't see what's going on to the right of x equals 4 in this window. So let's try to make the y's a little bigger. Expand this. Let's say maybe let's make it up to 20 and see if we can see anything. There we can. So we can see that this is actually a branch coming down through quadrant 1, coming from the positive direction, high y values, the closer we are to 4, and then coming down here. So let's sketch that much. And then that question about the horizontal asymptote was what's going on when x is large. So we want to zoom way out so that we can see for large values of x, what are the y's doing? So I'm going to expand this window greatly. I'm going to make it negative 100 to 100. And I'm going to make the x scale 10 just so the tick marks are nicer. And I'm going to leave the y values, I was going to say leave them like they are, but I think I'm going to move them down to negative 8 to 8 again. I don't want to see that whole branch that I saw before. Okay, so now I can see, alright, so it does seem that the y values are kind of leveling out. We could use our trace feature and go to the left and see what seems to be happening to the y values. They're still going up, up, up. So let's zoom out a little bit since it doesn't seem like they've leveled out yet. Let's make our window maybe negative 1,000 to 1,000 instead. And now it looks like the graph almost looks like a horizontal line. And if we trace again, oops, just trace. Still going up, still going up. Now they're not really going up so much. I'm still tracing to the left. They're just barely moving up. You can see it looks like they're getting closer and closer to 3, but they're just not growing very quickly anymore. It might be easier to see this in a table. Let's set up a table and go on the right side instead. So let's start our table at 2,000 and go up by hundreds. So starting at 2,000 and going up by 100, let's go look at this table. So it looks like we're getting closer and closer and closer to 3. Right? And so closer and closer and closer to 3 from both sides. So in the long run, and it doesn't happen all that quickly, the graph will get closer and closer to 3 on both sides. On this side, we're always going to be slightly above 3, and on this side, we're going to be slightly below 3. So our question is, so we used a table, and we looked at large values of x. And it appeared that the horizontal asymptote was y equals 3. So we added that to our graph, and we demonstrated that the graph to the right and to the left is going to get closer to that line, y equals 3. So our question is, how would we know that in advance? So how can we find the horizontal asymptote algebraically? And here's the key. So we're going to do this. We're going to look at this function, and we're going to divide both the numerator and the denominator by the highest power of x that occurs in the denominator. In this case, that's just x to the 1. So I'm going to rewrite this. It's going to look like a complex fraction, basically. We're going to have 3x minus 8, divide the whole numerator by x, and x minus 4, and then divide the whole denominator by x. So we've done the same thing to the numerator and the denominator. So officially, we just multiplied by 1, and we turned what was not a complex fraction into a complex fraction. And then let's reduce where we can. So now we've got 3 minus 8 over x over 1 minus 4 over x. It's the same function, but it just looks more complicated. But in this form, since we're interested in what's going on when x is large, this form, it's easy to see what's going on when x is large. So when x is large, either positive or negative, in this case, 8 divided by x is going to be closer to 0, and 4 divided by x is also going to be close to 0. So if I take 8 divided by a large positive or a large negative number, I get something that's really small. If I take 4 divided by a large positive or a large negative number, I get something that's really small. So the idea is that this is going closer to 3 as x gets large positive or as x gets large negative. And in this weird complex fraction form, that's easier to see than in this original form. So I divided, again, both the numerator and the denominator by the highest power of x in the denominator, reduced where I could, and then I looked at the pieces that still involve that x, and I said, what are these pieces doing as x gets large? And both 8 over x and 4 over x are going to be getting closer and closer to 0 as x gets large. So the function will be more or less like 3 minus 0 over 1 minus 0. So we could see that from the table and from our graph, but then we can also see it algebraically by doing this trick of dividing everything by the highest power of x that occurs in the denominator. So, when we want to sketch the graphs of rational functions, we want first to factor the numerator and the denominator, because the factored form will help us find the x-intercepts as well as the vertical asymptotes. So the x-intercepts will be the zeros of the numerator because if a fraction is going to be 0, its numerator needs to be 0. So the x-intercepts are always the zeros of the numerator. The y-intercept is the same as it always is, just put 0 in for x and find the function value. The vertical asymptotes are the places where the function is undefined, which will be the zeros of the denominator. So the factored form, knowing the factors of the numerator will tell us the x-intercepts. The factors of the denominator will tell us the vertical asymptotes. And then the rules for finding the horizontal asymptote, the trick is to divide the numerator and the denominator by the highest power of x in the denominator. And then think about what happens as x gets large. either large positive or large negative. We'll come back to the screen and we'll write down some general rules, but for now what we want to do is do exactly this. Divide the numerator and the denominator by the highest power of x in the denominator, and then think about what's going on as x is getting large. So, for this particular example, let's find the intercepts first. We'll start with the x-intercepts, and that's where the function is 0. And on the previous page, actually we want to get this factored first, right? Oh, we better change this. This doesn't factor, right? X squared plus x minus 3. We need something we can factor. So let's change this to x squared minus 2x minus 3. Which would factor as x plus 2 over x minus 3x plus 1. There we go, that we can factor. Okay, so the x-intercepts would be 0 equals x plus 2 over x minus 3 x plus 1. And on the previous page I had written that the x-intercepts were just the zeros of the numerator. And remember, here's why. If I have this fraction equal to 0, I can multiply both sides by x minus 3 x plus 1. And this is equivalent to 0 equals x plus 2. So we only care about the numerator 0. So negative 2. The x-intercept we want to list as a point, negative 2, 0, not as x equals negative 2 because that would be a line. The y-intercept would be f of 0. F of 0 is, in this case, 0 plus 2 over, this is probably easier to find in the non-factored form, so over 0 minus 3. Looks like negative 2/3. The vertical asymptote, or actually there's more than one in this case, are the places where the function is undefined. So in this case that would be x equals 3 and x equals negative 1, the zeros of the denominator. Because a function is undefined when the denominator is 0. And we list them as vertical lines, so x equals one number, x equals the other number. Then we want a horizontal asymptote. And we'll find it by doing what we said we were going to do, divide everything by the highest power of x in the denominator. And here you want to use the non-factored or the expanded form. Okay, so in this case, we would divide everything by x squared because there's an x squared in the denominator. So divide each term by x squared. So again, our process is divide each term by the highest power of x in the denominator. And that's going to give us, if we reduce things, 1 over x plus 2 over x squared over 1 minus 2 over x minus 3 over x squared. So as x gets large, either positive or negative, you want to think about what's going on with each term. 1 over x, if x is large, that's going to go to 0. 2 over x squared, as x was large, we will also go to 0. 1 will just stay as 1. 2 over x will go to 0. And 3 over x squared will go to 0. So huge denominators will make each of these fractions just go to 0. So this whole thing is going to be getting closer to 0 plus 0 over 1 minus 0 minus 0, which is 0 over 1, which is 0. So in this case, as x gets larger and larger and larger, the function values are going to 0. So the horizontal asymptote would be y equals, it's a horizontal line, 0, because the function values are getting closer to 0, which is just the x-axis. Alright, so now we've got all the information we need. We know the x-intercept is negative 2, 0. We know there's a y-intercept of negative 2/3, so that's a point. There's a vertical asymptote at x equals 3. There's another vertical asymptote at x equals negative 1. And there's a horizontal asymptote, so in the long run, the graph is getting closer and closer to the x-axis. So I'm going to put that dotted line out on the right edge and on the left edge. Now we just need to know, how are we going to put the rest of this graph together? And for now, let's take a look at a table on our calculator. Let's enter this function. And we'll enter x plus 2 divided by, and if you use the expanded form, you need only one set of parentheses, but if you use the factored form, you'd want to have a double set of parentheses because you need both of those factors in parentheses in the denominator. So I would enter x minus 3 times x plus 1 and put a set of parentheses around both factors like that. So now let's go to the table, and what I'm interested in is what's going on close to x equals negative 1. There's a graph, and we don't care about that. So let's start, let's just do ask instead of in auto. So we'll change it to ask, and we'll put in values that are close to negative 1. So let's do negative doesn't seem to be working, right? No, I don't want auto, I want ask. Okay, negative 1.1. We get like negative 2. Negative 1.01. Sorry, I said negative 2, but positive 2. 24.688. Negative 1.001. Larger still, 249.69. So I can see that as I to a little bit to the left of negative 1, I have large positive y values. And I want to go on the other side, so maybe negative 0.99 and negative 0.999. So using this table, I can see what's going on close to negative 1. We'll use this in a second for our graph. Oops. And let's do the same thing close to 3. So if I do this table close to 3, let's get rid of these values. So if I do, let's say, 2.9 and 2.99, and then 3.1 and 3.01, then let's take a copy of that. All right. So now let's take a look at what this helps us do on our graph. So to the left of negative 1, the y is getting large positive. And to the right of negative 1, y is going large negative. Right, so on this side we're going down, and on the other side we're going up. And around 3, it looks like to the left of 3, y is going large negative, and to the right of 3, y is going large positive. So we've got this direction to the left of 3 and this direction to the right of 3. That is enough information together with the multiplicity of the zeros to be able to figure out what the rest of this graph looks like. We know that in this middle part here, there aren't any x-intercepts in here, so we are not allowed to cross that x-axis. So this has to come up somewhere, hit a high point, and then fall back down, but not cross the x-axis. On the right side here, this rightmost branch, the same thing. The graph does not cross the x-axis because there aren't any x-intercepts over there. There's just that one x-intercept at negative 2. So this graph is going to come back down and get closer to this horizontal asymptote as x gets large. On the left side here, this x-intercept, there was just one factor. So we want to think about the multiplicity the same way we did with polynomials. It's multiplicity 1, so the graph crosses the x-axis rather than turning around. So we know the graph is going to cross the x-axis here, and then it's going to eventually come back up and get closer to this horizontal asymptote. We don't know how low it will go. That's something we could figure out with a calculator or when we get to Calc 1. But for now, we just know it's going to cross that axis and then come back and approach that horizontal asymptote. All right, so that's everything we need to know about that graph. Let's do one more example and then look at some more general approaches to this horizontal asymptote problem. Example 3, again, our goal is just sketch the graph of this thing, and we'd want to start by looking at the factored form. We can factor out a 2, and then we can factor that as a difference of squares, so x minus 1, x plus 1. And then our denominator factors as what, x minus 5, x plus 2. So we'll start listing the features and then go from there. So if we do our x-intercepts first, again, those are zeros of the numerator. So 2 times x minus 1 times x plus 1 equals 0. We can divide it all by 2, so don't think that 2 is itself a 0 of the numerator. We just have x minus 1, x plus 1 equals 0. So x equals 1 or x equals negative 1. So the x-intercepts listed as points are 1, 0 and negative 1, 0. And both of these are multiplicity 1 because the exponent is 1 for each factor. So the graph crosses the x-axis at each point. Because they're each multiplicity 1, which is an odd multiplicity. Then the y-intercept is f of 0, so put 0 in for x. You can use either form. If you use the expanded form, you have 0 minus 2 over 0 minus 0 minus 10, which is negative 2 over negative 10. A negative divided by a negative is a positive 1/5. You really want to be careful about the sign of your y-intercept because that's going to help you determine the shape of the graph without your graphing calculator. So if you have the sign wrong, a lot of things will fall apart. If you use the factored form, let's just take a look at that too. You'd have 2 times negative 1 times 1 over negative 5 times positive 2. Still negative 2 over negative 10. But it's always a good idea to look at both forms and make sure you're getting the same value, just as kind of a double check. So 0, 1/5 for the y-intercept. The vertical asymptote, or vertical asymptotes as the case may be here, are the zeros of the denominator. And these are written as lines, not points. The zeros of the denominator, this time we have x minus 5 times x plus 2 equals 0. So x equals 5 and x equals negative 2. I'm going to write down the multiplicities for these. And we'll talk this time about how to use the multiplicities to determine what's going on around these vertical asymptotes. So for now we just wrote it down. In a minute we'll talk about how to use that. So the x-intercepts we have, the y-intercepts we have, just one of them always, and the vertical asymptote. Then we need to talk about horizontal asymptote. So what we want to do is take the form that we're given, the expanded form, divide everything by the highest power of x in the denominator, which in this case is x squared. simplify, it'll still be a complex fraction. And then think about what happens as x is large. And anytime I have a number divided by a power of x, as x gets larger, that fraction is going to go to 0. So this will end up as 2 minus 0 over 1 minus 0 minus 0, which is just 2. So as x goes to infinity, the y values, the outputs, are going to 2, which means the horizontal asymptote would be y equals 2. All right, so let's put this all together. Our x-intercepts are points, so let's put those points on the graph, 1, 0, negative 1, 0. And we know that the graph is actually going to cross the x-axis at each of those points. We also have a point on 0, 1/5, the y-intercept. Those are the only 3 points that we know. Then we know some asymptotes. At negative 2 for x, we have a vertical asymptote. And at 5 for x, we have a vertical asymptote. And then there's a horizontal asymptote on the horizontal line through y equals 2. The horizontal asymptote, you don't want to draw all the way across the graph because that's only what's going on the edges of the graph, to the left and to the right. So you don't need to draw it all the way across. It's fine to cross the horizontal asymptote in the middle. The key is that you just need to make sure that the function is getting closer to that line as x is getting larger in the positive or negative direction. So now let's use what we know about the x-intercept multiplicities to at least sketch the interior part of this graph. Starting at the y-intercept and moving to the right, we know that we have to cross this x-intercept. So we know we're going to be on the negative side of the x-axis as we cross this x-intercept. And we also know as we approach this horizontal or vertical asymptote at x equals 5, we have to either go up to infinity or down to negative infinity. We're forced to go down to negative infinity because there's not a place to cross the x-axis over here. We've marked all of our x-intercepts and there's not one here between 1 and 5. So this graph has to go down on this side. Similarly, as we move left, so x less than 0, we know we have to cross this x-intercept because it's multiplicity 1. So we don't turn around, we just cross through that x-intercept. And there's not another x-intercept between this one and this vertical asymptote, so we're forced to be going downward on the left side of this asymptote at x equals negative 2. So we knew we had to cross the x-axis at each of these x-intercepts because of their multiplicities. And now the way we're going to use the multiplicities for the vertical asymptotes is if it's odd, we're going to switch sides, or switch signs, let's say. Just like when there's an odd multiplicity x-intercept, we switch signs. We can move from positive to negative or the other way around. When we have a multiplicity 1 or 3 or any odd multiplicity vertical asymptote, we'll switch signs from negative to positive or the other way around on either side of that asymptote. So here, if one side of this asymptote is negative and this is odd multiplicity, we switch on the other side and go to the positive side. Similarly, this one we switch and go up on the other side. If this had been, say, x minus 5 squared in the denominator, then the two sides would have the same sign. We would not switch signs. So, in the previous example, we used a table to get that information. Here, we're just using the multiplicity. We'll say, should we switch signs or not? If it's odd multiplicity connected with that factor, we do switch. If it's even multiplicity, we don't. So both of these just had exponent 1, so we do switch signs for both. We knew this side of x equals 5, the left side was going to negative infinity. We want to switch and go to positive infinity on the other side. And now we can finish the graph. We know this has to approach, as we move right, we have to approach the line y equals 2, and as we move left, we have to approach the line y equals 2. So there's a picture of the graph. So looking back at that previous example now, in light of the multiplicity discussion about these vertical asymptotes, both of these were odd multiplicity. So we want to switch and switch. On either side of those asymptotes. So you can see one side is down, the other side is up for each of those asymptotes. So we want to observe the multiplicity not for just the x-intercepts, but also for the vertical asymptotes. And in each case, an odd multiplicity means we're going to change signs, and an even multiplicity means we're going to stay the same sign, either positive on both sides or negative on both sides. Okay. One more example here. X minus 4 times x plus 1 would be the factored form of the numerator. And then the denominator is already factored as x minus 1. So if we make a list of all the key features, our x-intercepts are where the function is 0. Multiply everything by x minus 1. That means we just are really worried about where the numerator is 0. So x equals 4 or x equals negative 1. Both multiplicity 1. So we've got two x-intercepts, 4, 0, and negative 1, 0. Each multiplicity 1, so the graph crosses the x-axis at each one. So 4, 0, negative 1, 0. Y-intercept. Let's look at both forms. If we use the expanded form, we have 0 minus 4 over 0 minus 1. So negative 4 over negative 1, which is 4. If we use the factored form, we have negative 4 times 1 over negative 1. Same thing, that's good. So 0, 4 for the y-intercept. So we've got 3 points, 2 x-intercepts and a y-intercept. Then the vertical asymptotes. In this case, there's only one, the 0 of the denominator. And again, I'm going to write this question, where is f undefined? So x equals 1, and we leave it as the equation of that vertical line. And also make note of the multiplicity. There's just one of that factor. So we'll switch signs on either side of that asymptote. And then finally, we want to know about a horizontal asymptote. And in this case, we're looking at f of x equals x squared minus 3x minus 4, and the denominator is x minus 1, so we want to divide everything by the highest power of x in the denominator, which in this case is just x. So we want to divide by x, 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 and x, and x for each term, and simplify. This time that's going to leave me with x minus 3 minus 4 over x over 1 minus 1 over x. And as x gets large, y is going to be getting closer to, let's leave it as x minus 3 minus 0 over 1 minus 0. So this time we don't get a horizontal line at all. We get a slanted line. So as x gets large, either in the positive or negative direction, y does not approach a single value. Y approaches a line that's slanted instead. So y will get large or in the positive or negative direction, depending on which sign we have on our x, which means there's not a horizontal asymptote at all. The reason this happened was that the degree of the denominator was less than the degree of the numerator. So when we divided everything by x in this case, there was still a factor or a term of x left in the numerator. So as x gets large, the numerator is still just going to get larger and larger and larger. It's not going to settle down to a single value. So the reason for this basically is that the degree of the numerator is larger than the degree of the denominator. And in this case, anytime that happens, where the degree of the numerator is larger than the degree of the denominator, there will be no horizontal asymptote. And we gave a demonstration of that here. So let's go back to our graph. Knowing that there's no horizontal asymptote, using the multiplicities, we should be able to put everything together. Moving from the y-intercept, which is the point that we know that's not on the x-axis, if I go left, I know I have to cross this x-intercept because it was multiplicity 1. And I know this graph doesn't have a horizontal asymptote, so it's going to keep moving just downward. I know there's not another x-intercept. We just keep going down, down, down. As I move to the right of x equals 0, I know I have to cross, I have to either go up to infinity or down to negative infinity when I get to this barrier, this vertical asymptote. There's not an x-intercept to cross. There's no way across the x-axis, so I know it has to be going up toward positive infinity. Because this vertical asymptote was multiplicity 1, I know I'm going to switch signs. So if one side is positive, the other side needs to be negative. So this side will be down. Again, I need to cross this x-intercept because it's multiplicity 1. So when I get there, I'm not going to turn around. I'm just going to go straight across. And this side has to keep going up, 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 because there's no horizontal asymptote and there are no other x-intercepts to come back down to. So we've got the graph here of this particular rational function, using the multiplicities of the zeros and the multiplicities of the vertical asymptotes, and the fact that there was no horizontal asymptote. So let's go back to the screen where we had the rules for finding the horizontal asymptotes, and let's try to make some generalizations. So to go through the work and show an algebraic proof of why a particular horizontal asymptote is the right one, this is what you want to do. Divide the numerator and the denominator by the highest power of x in the denominator, which is what we've done so far. But it's okay to use some general rules, some guidelines, and not go through that work every time. We just saw if the degree of the numerator is greater than the degree of the denominator, then there's just no horizontal asymptote. None at all. We also saw an example where the degree of the denominator was greater than the degree of the numerator. Let's go back and look at that example and see what happened. And I think that was our third example. Nope, fourth. Where was it? Example 2, I guess. We had a degree 1 numerator, a degree 2 denominator. And in that case, what happened was we had a 0 when we divided by x squared, a 0 in the numerator, and a 1 in the denominator. So we got a y equals 0 for the horizontal asymptote. That will happen any time the degree of the numerator is less than the degree of denominator, or the degree of the denominator is greater than the degree of the numerator, because it means the denominator is growing faster than the numerator. Sorry. So if the degree of the denominator is bigger, the denominator is growing faster, so there will be a horizontal asymptote at y equals 0, which is the x-axis. So keep in mind, no horizontal asymptote, that's different from a horizontal asymptote at 0. There is a horizontal asymptote in this case, it's just that the value of it is y equals 0. So the key is to compare the degrees. If the numerator is larger degree, we don't have a horizontal asymptote. If the denominator is larger degree, we do. It's on the x-axis. If the degrees are the same, which is the only other option, then there is a horizontal asymptote, and the way we find it is to take the ratio of the leading coefficients. Let's look and see that that's what happened in our two examples in which the degrees were the same. So in example 3, both of these were degree 2, and the leading coefficients were 2 and 1. So if we look at that ratio, 2 divided by 1, that's exactly what we found for our horizontal asymptote. And the first graph we did, this one where we looked at it on our calculators, these are both degree 1. The ratio of the leading coefficients is 3 to 1, and we found that the horizontal asymptote was y equals 3. So we can see that that's what we were finding in our examples. So it is absolutely fine to use these guidelines for determining your horizontal asymptotes. You don't need to go through the work of dividing by the highest power of x in the denominator every time. MyMathLab is probably going to ask you to do that on a few problems at least, to just show your work of dividing everything by the highest power of x in the denominator. But on a quiz or a test, it's fine if you use these guidelines. Let's do one more here, and then I think I'll split this and do a second video for the rest of the examples here. So the next one, we've got x-intercepts the zeros of the numerator. So negative 3x equals 0, or x plus 2 equals 0, which means x is going to be 0 or x is going to be negative 2. Both are multiplicity 1. Which means our two x-intercepts are 0, 0 and negative 2, 0, and the graph is going to cross at each one. The y-intercept has to be 0, 0 because one of our x-intercepts was 0, 0. If you plug in 0 for x, you'll get, yes, certainly x equals 0 gives us y equals 0. So 0, 0 for our y-intercept as well. Then we want to know the asymptotes. The vertical asymptote would be the zeros of the denominator. In this case, there's just one. Remember, this is not plus or minus 1. It would be x minus 1 is plus or minus 0. So x is just 1, but it's multiplicity 2. That's what this squaring of that factor is doing. So we don't switch signs. At that asymptote. Then, last thing, our horizontal asymptote. We want to compare the degrees of the numerator and the denominator. Both are degree 2. So the degrees are the same. So we know we'll have y equals leading coefficient of the numerator over y equals, over lead coefficient of the denominator. The leading coefficient of the numerator, if I expand this, I'd have a negative 3x squared, so negative 3. And in the denominator, they would just be a coefficient of 1 on x squared, so negative 3 over 1. So y equals negative 3. So putting on our points, we've got 0, 0 and 0, negative 2. This time we don't have a third point because one of the x-intercepts is also the y-intercept. We've got a vertical asymptote at x equals 1. And if we make some notes, we want to cross at each of these x-intercepts, and we don't switch signs on either side of the vertical asymptote. Our horizontal asymptote, remember, is just on the right and left edge of the graph. So let's do this. And now we're at a strange spot because usually we've been able to start with our y-intercept, which is a point that's either positive or negative, has been in other cases, and then move from there. This time we don't have any points that are off the x-axis. We only have points that are on the x-axis. So we have a few options. We could use one or the other side of the horizontal asymptote and move from there. Or we could pick a numerical value that's not already being used, say like 2. Find the function value at 2 and use that point to continue. Let's do that. So just to get a point that's not on the x-axis, if I calculate f of 2, I have negative 6 times 4. So negative 24 over 1 squared. So negative 24. So I could call this negative 24. If we go by sixes, 1, 2, 3, 4, negative 24 here. And then if I move to the left of there, I know I have to, when I hit this boundary, this barrier, the vertical asymptote, I have to go down because I'm not allowed to cross the x-axis unless there's an x-intercept. And I also know that I have to level off at this line y equals negative 3 as I move to the right. So I've got this branch done. Then I say, okay, I want to go on the other side of this vertical asymptote. Should I go up or should I go down on the other side? And using that multiplicity, I say I'm not going to switch. So both sides are down since I knew this side was down. So I'm going to be coming up from down here. I have to cross my x-axis at the y-intercept or the x-intercept, whichever way you want to look at it. I'm going to cross and then come back down to the other x-intercept, cross that one, both based on the multiplicities, and then I'm going to level off at the horizontal asymptote on the other side. So I don't know what the high point is in here, but I know I cross both x-intercepts, and I know the behavior is the same on both sides of that vertical asymptote. So that has enough detail on the graph for something, for an activity or for an exam. Alright, so we'll quit there and then we'll come back. I'll start a different separate video for the rest of these examples.